Hello, everyone. Welcome to the seminar of the Astronomy Department of IAG-USP. Thank you all for your participation. And today we are pleased to have the presence of Dr. Teresa Antoja from Universitat de Barcelona in Spain. Dr. Teresa, thank you for accepting our invitation. Let me introduce briefly the bio of Teresa. She got her PhD in 2010 from University of Barcelona. Please correct me if I make any imprecision. And she worked as a researcher in the Captain Astronomical Institute in Groningen, the Netherlands, and later on in the European Space Research and Technology Center, also in the Netherlands. And since 2016, she works in the Instituto de Ciências del Cosmos of the University of Barcelona. Teresa's research is mostly related to the dynamics of the Milky Way, and she's also very involved in the Gaia consortium. Today, Dr. Teresa is going to present the seminar, A Perturbed Milky Way with Gaia DR2 and EDR3. And questions can be asked to Teresa after her presentation, or if Teresa prefers we interrupt, you just tell us, and we make questions during the presentation. And for those who are following the seminar on the YouTube channel, you can write your questions in the chat. I will bring it to Teresa after the presentation. And if you are using Google Meet, just push the hand button to indicate you have a question. I would like to ask everyone to turn off your microphones and cameras during the presentation. Teresa, please feel free to start.
Well, thanks a lot for the invitation. It's a pleasure to give this talk. Of course, I would have liked very much to be there in person and to see your wonderful country and see and meet you and discuss more in-depth things, but it is how it is, and at least we do it online, which is also fine. You can interrupt, of course, if you feel that you have a pressing question. Please interrupt. There's no problem. So I'm gonna share the screen. Do you see the slides?
Yes.
Okay. I will hide this. Sorry. I do again. Okay. So, well, this story, the one that I'm gonna tell you today about, it starts with a spiral shape, like this one here, that appeared when analyzing for the first time the data from the Gaia mission in the second data release. A shape that was not expected, that was not predicted by any model. And that's why we were a bit surprised to see it, and perhaps we even thought there could be some problem in the data or some strange correlation that we had missed, but that we saw later with some analysis that it's a true shape, it indicates that there was a perturbation in the past in our galaxy. So this plot, this spiral shape that appeared in this plot, it's a representation of the vertical phase space of the galaxy, of the solar neighborhood, where we have in this axis the Z coordinate, so how the position of the stars below or above the plane, and in the vertical axis, the vertical velocity. And we see when we paint the stars as a function of their rotation velocity, the rotation around the center of the galaxy, we see this very nice shape appearing that, as I said, was very surprising. So I will talk a bit about the story of this spiral and what it means. This is a bit the outline of the talk, some introduction. I'll speak very briefly about Gaia, this phase spiral and the possible relation with the Sagittarius dwarf galaxy. And I'll talk at the end very briefly about other disturbances apart from the phase spiral that have been detected by Gaia, and what do they tell us about the past or the present of the galaxy. And finally, some remarks, and talk a little bit about the future. Some introduction. First of all, let me show this slide where we can see all the faces now that we don't travel and we don't discuss things face to face. It's important to show that there are always people behind all these discoveries, this research, these missions, and this data, this so big data sets that we have. So first of all, Gaia DPAC, the consortium that have prepared the data processing and the validation with more than 400 people all around Europe. And here our group in Barcelona, which is a mix of engineers and mathematicians and working directly on the data processing, but also scientists as me. And also a few collaborators that are not in Barcelona, but also important in what I will be showing. So let me start with this beautiful picture, the Hubble Ultra Deep Field, beautiful and also meaningful, because we see here all these galaxies with different shapes, different colors, different orientations that are the building blocks of our universe, and that, of course, are relevant for this, one of the most important questions in modern astrophysics, which is how do galaxies form and evolve? One of the questions that was identified by this science vision for European astronomy in the past, and that we are still trying to answer. And in the context of this question, of course, there is the Milky Way, our galaxy, that can be used as a laboratory to try to answer this question, how do galaxies form and evolve, with the obvious disadvantage that because we are inside the galaxy, we don't get these beautiful images that we can get for other galaxies. And it's difficult sometimes to figure out what's the shape of our galaxy, but with an obvious advantage of getting individual information of individual stars, like positions, velocities, or properties like chemistry, which help a lot in this process of trying to understand what's the structure and what's the past of our galaxy. This is an image made by joining 50 different wide-angle images made from Earth. We will see later the comparison with what Gaia has obtained. With the years, of course, in the study of the Milky Way, even if there is this projection that complicates, projection effects that complicates this, we do have we have figured out a little bit about the structure of the Milky Way. We live in a disk galaxy. Seen edge-on would be something like this. This is just a cartoon image of how it will be. So most of the stars and the light coming from the disk. This is presumably surrounded by the dark matter halo. And seen face-on, we could see something like this with a bar, some spiral arms. This is, as I said, just a cartoon because we don't really know exactly how is the spiral structure of our galaxy, or how, for instance, how spiral arms are formed. It's a question that remains unanswered still today. I've seen in the audience somebody that have spent many, many years trying to understand what's the spiral structure of our galaxy. And of course, we in the last years, we have seen that the Milky Way is not alone. It's surrounded by other galaxies, which can be very relevant for its evolution, as we will see today. So this is a kind of zoom out where our galaxy is here in the center, and we have other dwarf galaxies, Large Magellanic Cloud, Sagittarius, other ultra-faint dwarf galaxies around that might at some point be important for the evolution of the Milky Way. This image also helps me to define a little bit the coordinates that I'll be using, cylindrical coordinates, since we are in a disk. Bz, the vertical velocity of the stars, how they move up and down, and the velocities on the plane, so b phi, how the stars rotate, the velocity of rotation around the center, and br, the velocity of the stars moving in and out. And the important point here of all the presentation and of most of the studies I've been doing since my PhD is this idea that the phase space coordinates can help us to do a diagnosis of the Milky Way. And I'll show several examples, and let me start with some observations before Gaia, for instance, with the Sloan survey or with RAVE that measured for the first time radial velocities for a large number of stars in the galaxy. And in this plot here, for example, we are plotting Bz, so the vertical velocity, as a function of z. And we would expect for a galaxy that is in equilibrium that this is completely zero at any z. The vertical velocity should be zero if it's a disk that is in equilibrium and it doesn't suffer perturbation. Instead, we don't see that it's zero. We see some clear signatures of positive and negative vertical velocities depending on where you are. And so there is this asymmetry and some velocities that were not expected in equilibrium. Similar thing is seen in rave. And for many years, we've been already debating if this might be due to external perturbations or if these are just signatures or some internal modes that can develop in disks like spiral arm spars, etc. So Gaia, what is Gaia? I guess most of you know, so just very briefly, this is the satellite, how it looks when it was being prepared at ESA. And these are the different instruments that the satellite has on board, the CCD detectors, photometers, spectrograph, and all the different quantities that you measure, like positions in the sky, parallax, so proper motions, all the astrometric solution that is obtained from the detection on these CCDs, and also the magnitude G, some other quantities, colors, and other photometric quantities coming from the photometers, and radial velocities, chemical abundances, and with all this, we get this very large catalog of stars that has allowed us to go from these kind of maps that we had from Earth to something like this. This is the image that came with the second data release of Gaia, which is like a composite image joining all the points, all the stars that the Gaia catalog has, and painting by colors, the colors measured by the mission. And also showing this other plot, which is the image that is not an image anymore, it's the movie that came with the third data release, the early third data release in December 2020, where we are also illustrating the fact and the treasure of the Gaia catalog goes beyond a pure map, because it measures these velocities that you can see here in these lines, tracing the path of the stars on the sky, and which, as I said, it's at least to my work, it's the fundamental piece, measuring all these velocities, and we'll see why. In terms of the region we cover of the galaxy, we can see in these maps very quickly the region for which we had in the past measurements of the 6D space positions, 3 velocities, 3 positions for all the stars, which was really, really small around the solar neighborhood. After the arrival of other surveys such as RAVE or SLOAN, this volume grows a little bit, and now with Gaia, we can tell we have this 60 phase space sample covering a large region. Of course, this is approximate because it depends on the magnitude of the stars and so on, but just a schematic view of the region for which we have data, 6 million stars that have all the measurements of the positions and velocities with incredible errors, and that is also one of the key pieces in what I've shown, in what I will show later, because errors are of the order of 1 kilometers per second, while there used to be around 10. And it's exactly this large number of stars and this high precision of the measurements that allow the discovery of these structures in phase space that we've seen in Gaia. For instance, in the vertical phase space, the one I shown before, Z, BZ, in the past, where we didn't have Gaia DR2, the map would look something like this. After DR2, you can see already that there is some signature of a spiral shape here, kind of correlation between Z and BZ, that maybe if you don't see it very well here, some other people applied some image filtering, and you can see that the spiral is appearing here very, very clear. But also when you do the same projection, but now paint it as a function of the other velocities that we have, BR and B phi, we see very clear, especially in B phi, this shape that in the past was just simply not observable due to the number of stars and the resolution and the precision of the data. So this was, as I said, very surprising, because it was not predicted by any model that we would find something like this in this projection, and we had to figure out what was going on. And to give a brief explanation of what happened, basically we need two ingredients. We need to have two ingredients clear in mind. The first one is how are orbits in the galaxy, and in the vertical part, we know they follow some oscillation, something like this. This is also a cartoon, but it could be something like this. And so consequently, in the BZ space, this is the space that I'm talking all the time about, a single star would do revolutions around the center, right, with the corresponding turning around points, or the crossing on the midplane corresponding to this position around this oscillation. And as a first approximation, one can say that the period, so the time it takes for a star to do a whole revolution in this vertical phase space, depends on two things. Depends on the radius of the galaxy, or where they are. So stars that are in the inner parts of the galaxy have higher frequencies, so shorter periods, compared to stars that are in the outer parts of the galaxy here. But the period of the oscillation also depends on the vertical amplitude of the oscillation. So, for instance, a star that is following a larger oscillation around the center takes longer to do a whole revolution. The equivalent of this with a pendulum, that perhaps is a system that we all physicists know, would be something like this. So in the first approximation, the harmonic oscillator, basically the pendulum only depends on the length of the cord, and this would be something similar to R. But as a second order, it also depends on the amplitude of the oscillation with this theta zero, so the initial amplitude, which is equivalent to the amplitude, the vertical amplitude of the oscillation. So we have, this is one ingredient that we need to understand why we get a phase spiral in this projection. The second ingredient would be something like this. What happens when a galaxy, small galaxy like this, perturbs a disk like the one of the Milky Way, for instance? You can see that especially in the outer parts, maybe I'm going to play it again, especially at the outer parts where the satellite is approaching, you see this displacement of stars above or below the plane, right? That follow, of course, the gravitational pull of the satellite, right? So if we would now look at this thing, at this galaxy seen phase on, and we do a map, for instance, of the Z mean velocity, the Z position, at each position of the disk, we would see parts of the disk, for instance, here with positive Z, so where the disk has been shifted like upwards, and places with negative Z, the disk has been shifted downwards compared to the original midplane, let's say. So when something like this happens, or some perturbation triggers a situation like this, let's imagine we now focus on a volume that would be around this position of this galaxy, around here. If we look now at the vertical projection of phase space of this position here, we could see something like this. For instance, stars that are globally centered at negative Z, instead of being centered at 0, 0, and more or less isotropically, that would be what we expect for a galaxy that is in equilibrium. But instead, we would find something like this. So now let's join these two ingredients. So after a certain perturbation, we might be in a situation like this, where our stars are shifted with respect to the center. And the second ingredient is the one I have told you before. Each of these points will do a revolution around the center, but each of these points will do this revolution with a different period, depending on the radius where they are and their amplitudes. So mostly stars that are here are on larger amplitude oscillations, so it will take longer for them to do the whole revolution compared to these inner stars. And we also know that in the solar neighborhood, there have been stars migrating in and out. So at the current volume right now, we might be having stars that most of the time spend their orbits on the inner parts of the galaxies, and some stars that most of the time are on the outer parts of the galaxy. So we have a mix of radius, of guiding radius or average radius currently in the solar neighborhood. So we have these two reasons for having very different periods here in this plot. So if we now evolve this with time, we will see that stars here in the very center, the ones with lower amplitude orbits, will do more revolutions compared to the outer parts. And this is like a continuous process. This now is evolving with time faster. And basically the structure stretches in a way of creating this shape. So this is a process of phase mixing where, due to the different frequencies of the stars, the original structure can stretch out, in particular to have this spiral shape, which looks very similar to what we see in the data. So it was clear then at that point that what we see is a signature of a phase mixing process. And then one can even try to estimate when this thing started. So when we were in a configuration that was ideal for this process of phase mixing to start. You can do this by applying a very, very simple formula. And for instance, if you take two stars here that are on two consecutive turns of the spiral, and you know their frequencies, which we can estimate assuming a certain model for the potential of the galaxy, for example, and know what their vertical frequencies are, we can just apply this to estimate that this process of phase mixing started about 900 million years ago. So something happened, and now here at this point we were wondering, okay, what is that we know that happened around that time? Do we have any evidence for something important at that time? And the most likely candidate was the Sagittarius dwarf galaxy that is now. So now this is a vision of the galaxy seen age on. The Sagittarius dwarf galaxy is here, but its orbit, its predicted orbit, could be something like this. So at some point in the past, the galaxy was also quite close to us in one of what we call the pericenter passages. It's now also close to one of the pericenter passages, but most of the models seem to indicate that the previous pericenter could be something around 1,000 million years ago, 800 million years ago, so compatible with what we see. So with this thing, we made the link, and of course, at that point, this was just a candidate because it was just a time coincidence of the two phenomena. This was a very, very nice discovery because not only because we are learning something about the past of the galaxy, something that might have occurred in the past that was very important for the evolution of the galaxy, but also in more practical terms, it's nice because we can use this to constrain, for instance, the perturbed orbit or the mass, because you expect stronger phase spiral if the mass is of the perturbed of Sagittarius is larger, for example, or even constrain the potential of the Milky Way, because as you see, the frequencies of the stars are important in all this problem, and the frequencies are related to the potential. And so this would mean that in a way we can even constrain the potential of the Milky Way. After the first publication of this, there were many people looking at models to confirm that Sagittarius indeed could be the culprit of this perturbation. And for instance, there is the model by Shervin Laporte, which is an n-body simulation of the interaction between Milky Way and Sagittarius. And you can see in one of the snapshots of the simulation that you see very similar shapes appearing in the vertical projections. Of course, the resolution is worse in the simulation than in the data, because now the data is, we have so many stars that it's always better than the simulation, which is somehow curious, but it is like this right now. But the shape is obviously there, so Sagittarius was a very, very likely candidate. There have been other alternatives, suggesting, for instance, that the bar buckling, which is something that we know happens usually in galaxies and in the Milky Way in particular, that has some vertical bending modes that can propagate in the outer parts of the disk. And this can also be the seat of having this not uniform distribution in the ZPZ plane that ends up forming the phase spiral. We also have other possible origins of bending waves that they will all lead to phase spiral as well. For instance, if there were many dark subhalos perturbing the disk, you could also create this sort of thing. So there are several hypotheses on the market, let's say, but I think the most favorite one is, in general, the effect of Sagittarius. There are problems, though, even associated to that, because it seems that you get, from the models, you really need a very, very high mass of Sagittarius to produce this, a mass that seems to be higher to what we expect or that what we see in this galaxy. So this might be a problem, but we are working to see what happened. And for instance, in order to do this, we started recently to look at cosmological simulations. So before this, only models like pure N-body models without gas or simple models with only one impact approach, for example, were used. And we thought it was important to use more realistic or sophisticated models, for instance, including gas, or being cosmological, like this one, or the two things at the same time, like this one. This is a simulation called Garrocha by Santi Rocafabrega. It's a zoom-in cosmological simulation, and we were curious to see whether there were phase spirals or not in this model, because the resolution of the simulations, of course, it's not very high. Otherwise, they already take months, as some of you may know. So the resolution is limited. So it was possible that we didn't have this. In fact, nobody else have been showing phase spirals in this type of simulations. So we were exploring the disk that is more similar to the Milky Way, this one, and that has several perturbers around, these little blobs that you see here. So what we do is we study the disk. Now you have it seen phase on here, and we study a certain radius, and we look at these different azimuths, so 12 regions at a certain radius, and we look at the vertical phase space projection of these regions. And that is more or less what we have here. So these 12 figures of one of the columns are the vertical phase space ZPZ of the simulation. And you can see, of course, with much poorer resolution compared to the data, but you can see that there are some spiral shapes appearing here. So this was already a very, very nice result. And in the simulation, so now the different columns show different times. So we can see here how this phase spiral evolved with time. And we see that there are still phase spirals even at other times. And in fact, we can even look at all the times of the simulation, because the simulation runs from redshift 6 or something like this. So we do all these things, 6 gigayears, sorry, I said redshift. 6 gigayears, more or less, is the time that we have studied. And this is the plot, so the 12 different regions and as a function of time. And you can see it's very small, but you can see that there are structures and spiral shapes in these projections in many of the times. And in particular, where we do have one of these little blobs, so little galaxies approaching, they seem to be stronger. These approaches are marked by these vertical lines here. And for instance, we see here very clear spirals, and here again. So it seems that where there is one of these approaches, the phase spirals look stronger. So it looks like they could be the cause in these simulations of the phase spiral. What we find, and that is curious, is that these the perturbers, these dwarf galaxies that we have, are of lower mass, of low mass, like 10 to the 8, well, it doesn't matter, lower than what other models have shown to be needed to produce a phase spiral. So it seems that here we do have low mass, but we do have spirals, as you can see. So now it remains to be seen what is going on in this simulation that makes it possible to create spirals, even if the masses are small or are smaller. And maybe it is because we have several perturbers at the same time, or maybe some dark perturber that we are not seeing, or maybe there are self-gravitating modes in the disk that are important and that can also create phase spirals. So there is a variety of things here. Also in the simulation, there is star formation, there is gas. So maybe the gas or the new stars keep the disk cold, and this makes it more likely to suffer these perturbations, and that's why we see it even if the masses of the satellite are a bit small. So we are now in the process of finding what is happening, and it's not easy because the simulations are really a monster with many different things happening at the same time, and we need to dissect somehow the different perturbations. I will skip this. It's important also to study the phase spiral in the context of these simulations that have gas and star formation, because other works, recent works, for instance, by Thomas Ruiz Lara, have shown that there are, independently of Sagittarius, when they study the star formation history of the disk, they see peaks of enhanced star formation. And again, looking at coincidences in time, they see that these peaks seem to coincide with the pericenter passages, so previous pericenter, the previous, and even the previous. And this seems to be matching, and it's something we have seen in models, that when there is a satellite approaching, you can also have starbursts. And that might also be the case of the Milky Way, and it's good that we can study all these different phenomena that are related, phase spiral, star formation, in the Milky Way, and also in models like the one I've shown of Cosmological Simulations. Maybe I will rush up a bit. Perhaps I can summarize a little bit this little part. So the Milky Way seems it was perturbed in the past, most likely by the Sagittarius dwarf galaxy. And this is nice. We can constrain the perturber orbit, its mass, the potential of the Milky Way. There is a kind of implication that the Milky Way definitively is out of equilibrium. And of course, all the modeling that we have in, classical books, like Jeans equation or something like, all these, assume most of the time that we are in equilibrium. And so people have been testing these equations in the situations where we are not in equilibrium. And of course, now we have problems. So this is a challenge to classical dynamical modeling. And we have several teams right now trying to see how can we solve this, and how we can include these equilibria terms in the Jeans equation, for example, or how do we model the galaxy in general when we know there are all these strong perturbations. Let me talk now very briefly about other disturbances. Apart from the phase spiral, there are other disturbances that have been measured by Gaia. These plots that I'll show in a minute come from the science verification paper that we did, that comes with every release. There is a series of papers trying to demonstrate the scientific potential of the data, and validation and performance and all this. And one of the papers of the last release in December 2020 was the Galactic Anticenter. And what we do in that paper, because of the difference between DR2 and EDR3 is only astrometry, there were not new radial velocities. So we wanted to focus on the improvement on the astrometry. So we chose to start to look at stars in the Galactic Anticenter. And in that direction, it's special because only with astrometry, parallax, and the two proper motions, you can already compute Bz and Bφ, the velocities in cylindrical coordinates. Not BR, of course, because this would be directly the line of sight velocity, but at least these two components. So that's what we did, and this is another projection of phase space, different to the one I've shown before. Now this shows Bφ, so the rotation around the galaxy, the velocity around the galaxy, versus the radius. We can see now in this sample towards the Galactic Anticenter that we have these very clear lines, diagonal lines that we now call ridges, diagonal ridges or whatever, that were already discovered in DR2. This was not new. The nice part of this last paper is that because the data is better, we can detect these things much better. This image here in black and white is a kind of image filtering to highlight the substructure that you have here. So it's the same plot, but just to highlight the lines. And in color, you have the lines, the ridges as they were detected in DR2. And now you can see that some of them, we are able to detect them farther away in the galaxy, so at larger radii, and we even see new structures appearing. So all this region here, let's say it was not covered in the past releases, so it was very nice to be able to reach and determine the kinematics at this very, very age, because this should be 16, 18, this should be the very age of the disk. So it's very interesting, it's very exciting. So apart from this, that is more like data improvement, what is now the cause, or what can be the cause of these reaches? And now this complicates the picture a little bit more, because we have several explanations again on the market. First explanation, resonances of the bar and the spiral arms. We know that when we have a bar, for example, there will be special preferential orbits where stars tend to be trapped to, and this basically creates a ridge in this projection. This is the same projection as with the data, but with an onboard simulation that has a bar. And you can see these lines appearing, and you can do orbital analysis, and you see that those are, in fact, stars trapped in resonance. So this is one hypothesis, so more like internal origin of these ridges. Second idea, we can have a perturbation, again, by an external galaxy, perhaps Sagittarius, the same perturbation that caused the phase spiral, maybe. Maybe it's also the reason why we do have these ridges. You can see here a simulation with a certain perturber, and you can see ridges appearing. They are stronger if the mass of the perturber is larger, which is something expected. So another explanation, more explanations. Phase mixing of transient spiral structure. If the spiral structure in the galaxy is something transient, like we see in most of the simulations, that it goes, disappears, forms and disappears, this would also create features like this. So we have, I think there are even more, but I don't want to complicate things too much. So we have several explanations, and it's really important, and that's what we are trying to disentangle between the different processes. More perturbations that we see in Gaia, and I won't show more because this can be too heavy. So now instead of showing like histograms of all the stars, here it's just the mean, let's say the mean B phi as a function of radius, or the mean BZ as a function of radius. So the black curve is for all the stars, and we have separated in two groups, stars that are above the plane and below the plane. And what we see is very interesting because they do not follow exactly the same patterns. So stars below the plane, that are the blue curve, seem to be rotating faster and seem to have larger vertical velocities. Instead, the ones above the plane, they show a different behavior. So it seems that the symmetry is broken. Stars above and below, they move differently. And we do have a coupling between all the components that we are showing here, B phi, radius, Z. So it looks like the whole phase space is perturbed in patterns that are difficult to understand, even to visualize somehow. And we need to figure out, well, first of all, to understand these patterns because they are complicated in this 6D phase space. And second, to disentangle or to find out which effects are causing them and what are the important factors influencing the evolution of the galaxy. So as important points of this little part, I think we can claim for certain that both external and internal mechanisms must be playing a role, because we know there is a bar, we know there are spiral arms, we know there are satellites. So how all the things combine together, it's a very interesting question. Can we disentangle between the two? Or even to make it more complicated, are spiral arms and bars excited by external perturbations? This is some hypothesis that is being there for a while. Why not? Maybe this is the whole scenario is a single thing, but seen from different point of views. And that is what I'm trying, and me and many people trying to find the answer to those questions. I'm just finishing. I think it's on time already. Some final remarks. I just want to show this picture because it shows the importance of Gaia in general, in reconstructing the history, the full history of the Milky Way. So this is a kind of family tree of how the Milky Way has been growing by different accretion events. I've been talking about Sagittarius, which is most of the recent ones, but just want to give the full context and tell you that, thanks to Gaia and spectroscopic surveys with the chemistry, for example, we have been able to even suggest particular accretion events in the past. So this interaction between galaxies, not only with Milky Way and Sagittarius, but other interactions that went on farther away in time, like 10 gigayears ago, for instance, with Gaia and Enceladus. And this is, I think it's very, very exciting that we are being able to do this. And of course, the future is looking very promising as well. As we speak, Gaia is there on the sky, still surveying and doing the revolutions to scan all the sky, to detect new sources, to detect more transits of the same sources, so to get better measurements, more accurate and precise measurements. And we expect for the first half of next year, so very soon in time, the third data release that now comes with, especially for many new products, but especially for my field, very important would be this 33 million radial velocities compared to the 6 million that we have, or 500 million astrophysical parameters, including not for all the stars, but for subsets, including metallicities, radii, luminosities, and so on. So, of course, again, we expect, I think, a nice moving forward in this next release in the next year, which will happen very soon. Also, other surveys I'm participating in are WIF, which will measure radial velocities for the stars that are too faint for Gaia to measure line of sight velocity. So Gaia has a limit in the spectrograph of about 16 magnitude. And so we are planning all these follow-up surveys that will measure this, and again will allow us to extend this place or this region that we cover with full 6D information, and more or less something like this, as you can see in this cartoon. And let me finish. I will skip this because maybe it's a bit late. And just let me finish with this nice quote by Antoja, who did one of the earliest simulations of interaction between galaxies, like this one interacting with this other small galaxy and creating these spiral arms due to this interaction. And they have a very nice sentence in the paper that say, "We conclude that here, as in medicine, pathology seems instructive." And I think this is a bit, I hope I've shown you that this is indeed what we are doing. So we are detecting some pathologies that we see in the phase space of the Milky Way, but using them as an instructive way to build or to be able to infer what was the past or the present structure and the past evolution of the galaxy. So we are using this in a very nice way. And with this, I finished. And thank you very much for your attention.
Thank you, Teresa. Very clear and very intriguing, the facts you showed today. When we think we had listened everything about Gaia, so there are always new, very interesting stuff that we can learn from. Now we'll start the discussion. The first one, Professor Jacques, please.
Okay. Thank you, Teresa, for your very nice talk. You are bringing new results that are very intriguing. I always admired your work, let us say, all your maps of the moving groups that you published several years ago. I have cited them quite often, and they are the only good data that we can find on them. However, I have a restriction on the spiral that you present, let us say. with a group at my institute, Tatiana Michenko, Douglas Barros, we looked into that, and we reached a conclusion that we don't want you to take it as an offense. It is what is it is. Let's say the word is artifact. The artifact is something that happens quite often, let us say, because when you have oscillation of stars in one direction, in the other, they can combine. And this is what we did, let's say. We took out from the data that produces the spiral, the moving groups. The moving groups, let's say we have the Coma Berenices, Pleiades, Sirius, and then to leave only the stars that are, let's say, considered to be normal stars of the disk, and then the spiral disappears. So it is a kind of coincidence. I must add also, let's say you have a plot with two axes. On each axis, the unit is different. One is velocity, the other is distance. So you could multiply by 2 or 3 or 4 the scale of one axis, and you will get a kind of very elongated spiral that does not look anymore with a spiral. Just a comment like this.
Well, I think so. On your first point, I think, and I've read your papers, of course. I think that the problem when you subtract the moving groups, since most of the stars on cold orbits seem to be on moving groups, when you remove them, I think it's very normal that you don't see the spirals anymore. But I agree with that. But the point, then let's look at the other way around. When we look at stars on moving groups, which are the vast majority of the stars that we have, they are organized in a phase spiral. So this means that moving groups were affected by this phenomena as well. That's the interpretation that I do of your findings. So it doesn't worry me in this sense. So I do this interpretation. That's for one thing. And the other thing, it's true that if you change the normalization, you would get something stretched, but you won't lose the spiral shape. It's just that it will be an elongated spiral, and of course, depending on your axis. And in fact, when you look at the phase spiral at different positions of the galaxy, that is exactly what you see, and it's what you expect because of the potential at the outer parts is lower, so your spiral stretches in one direction and in the other direction when you look in the inner parts, but you still see the shape. It's not roundish anymore, but you still have spiral shape. So I think, yeah, I don't know. Maybe this is something we can discuss one day in more detail. But
okay, thank you.
To you for the question.
I have myself some questions. Let's like to make one about it's not. I'm very curious about this relation, this perturbation when, let's say, Sagittarius pass by the Milky Way. So it would produce these oscillations also in the gas and in the stars.
I'm getting this question lately very much, and everybody seems to be suddenly interested by gas. We are looking at it in the cosmological simulations because we have it. So we see the gas is perturbed, but we are not yet. I cannot yet tell you that is the same perturbation. So we are trying to study how this is, and of course the response of the gas is different, and in general gas dissipates. I'm not an expert on gas, so if there's somebody in the audience and I say something weird, please correct me, but the idea is that gas dissipates faster, and so any perturbation that can be imposed on it will disappear faster than for stars. So, and that's why things can be complicated. But one interesting thing derived of what you ask is, and in it some other hypothesis going around, is, okay, what happens if gas is also perturbed, and from this perturbed gas you form stars which are born with this perturbation. So then the gas will dissipate, and maybe if the gas has been shifted like this, they will quickly fall again onto the plane, but not the stars that have been formed from that gas. And this is something we want to study as well. And so you are asking to me the most interesting question right now, and it's something we are looking at with the simulation. And with the data, there is some sign of vertical perturbations in the gas. And we are also trying to see if they look similar to what we see in the stars. It's not easy because, of course, how you measure velocities in gas is much different to how we do in stars. And we cannot do the exact same map ZPZ that we do for the stars. So we are trying to figure out if what we see in the gas looks similar. So I'm working on these two avenues, and I cannot give you a it's very, very interesting.
Yes, something extremely interesting for study of star formation, because probably it induces turbulence, and it would be marvelous to characterize the properties of turbulence and compression. But from the point of view of the global simulations, it's very hard because the dissipation is too much in the simulation. Maybe
that of course is a problem, but at least, for instance, to see what's the initial gravitational perturbation. Let's see, this should be okay. Right. How star formation occurs after that, it's more complicated. Yeah.
Oh, thank you. I have more questions, but first, Maria.
Yes, thank you. Thank you for your talk, Teresa. I have a question also related to star formation, because you mentioned that you see a triggering in the star formation when the dwarf galaxies are closer, let's say. How is actually this happening? Is actually because of the compression of the gas, or what
I think so, and I insist that I'm not an expert, but I think simulations show exactly this, that you have a kind of compression that where you get more star formation. But we are not sure. We see it in our model, but we really haven't got to the point of looking at the exact reason. But this has been shown in other simulations that it is the case. Yeah.
Okay. So we have to wait a little bit.
We have to wait, and
yes.
it's work going on, and hopefully we can. Yeah.
It's really interesting. Well, I have another question that is a little bit. I don't know if it's a correct question. Actually, I am wondering if there is another galaxy other than ours where you can see dark galaxies perturbing the shape of it.
Yeah, that's a very good point. So actually, I had in the slide in the. So can I share? Can I share again?
Yeah, sure.
Maybe it's faster if I explain it like this. For instance, I wanted to show these two plots. This is for a galaxy that I don't even know, BB304A, and they have measured very recently. So this is from Facundo Gomez, 2021, and they have measured, I think, from H alpha, the vertical velocities, because you are seeing these galaxies in phase zones. So the line of velocity tells you more or less about BZ. And you see these regions of vertical negative velocity and some regions with positive vertical velocity, which look very similar to this configuration. Where is that? To this configuration, for instance, here, and very similar to what we see in the models. And so we call them vertical corrugations, and this could be something similar, actually, something very similar. This with respect to some kind of vertical perturbations. Yeah.
Okay, so I guess it would be impossible to detect if there is a dwarf galaxy in there also?
I think there is a perturber. I forgot. I should refresh the paper. I'm not in that paper. I should refresh it. But I think they do have some candidate galaxy perturbed. I forgot the details, but I think it matches with this scenario. Yeah.
Great. Okay, thank you very much.
No, it's very interesting because, sorry, I had to rush in the end, but I always put this slide because, I think galaxy interaction studies in external galaxies have been going on for years and years, only with like images that you see very well, these tidal arms, you see lopsidedness, you see shapes, shells, anything, right? And now we are on the same, now we are starting to be able to study this for the Milky Way, which is cool. And in the same time, for external galaxies, we're getting to a point where we can do kinematics of this perturbation. So you see, we are doing the whole turn. And I think that's how we will really learn about all these phenomena if we study it from multiple points of view, right?
Yes.
So it's very interesting.
Yes, sure. Thank you very much.
Thanks to you.
Okay, Guilherme, please.
Don't you want to ask first, Reinaldo? I know that you have more questions.
I can ask after you.
Okay, so thank you so much, Teresa, for accepting the invitation again, because now it's nice because now we have a seminar about the bulge, a seminar about the halo, and a seminar about the disk this year.
So you are complete. You have the complete picture.
Yeah, the complete classical components. The question that I have is, I have actually many, but the first, I think the most important would be the most obvious, perhaps. The model from Laporte that you showed, it needs a very heavy, let's say, Sagittarius dwarf galaxy. Does it account, if we, for instance, measure the mass of the nucleus of the galaxy that we observed today, and we compare with the predictions from the models for the mass loss to the stream, can we reconcile the two things, or has anyone tried it?
So this is curious. So in principle, the nucleus, they say now that it's like 10 to the 8.
Yeah. But I think it's the stellar mass 10 to the 8.
No, it's like 4 times 10 to the 8 total, and 1 time, something like this. Doesn't matter, but it's 4 10 to the 8, so it's small. Then the problem here, and again, I'm not an expert on streams or on modeling of Sagittarius in particular, but for instance, this measurement, I think it was. So for instance, they with like abundance matching and this, they say that in the past, so before infall, maybe it had 10 to the 11. That is possible. Okay. Then the problem is to see what happened in between, right? 10 to the 10. 10 to the 10. The problem is what happened in between, and at a certain pericenter, how many mass did it lose already, and if it matches. So these studies of Laporte, they say, and others, that at the moment of pericenter, you need to have 10 to the 10.
Okay, the moment of the last pericenter.
And the last pericenter, but there is also discussion on whether this was the last or the one before the last. So then all these different, there are so many uncertainties that but they say it looks, so even if it's hard to decide in all this, the history of mass loss in all the life of Sagittarius, it seems that this 10 to the 10 at the moment of pericenter is a bit larger than what we would say according to the current star of the nucleus, to the current mass of the nucleus. But I'm a bit lost in this discussion too, because I'm just working on it from the indirect effects that this would have. And I don't know, maybe you know even more than me about this, but it looks a bit higher than expected, even when we take the whole thing into account.
Okay. Yeah, and the other question that I had is, do we have enough data to see, quote unquote, the evolution of the phase spiral, with the radials from the center of the galaxy?
This has been done, and there is this nice thing that you see. This is what I was discussing before. So you see at the outer parts the shape of the spiral gets a bit a bit like shallower, and in the inner parts it gets stretched like this, and this is due to the difference in the force of the vertical force of the galaxy, so the different frequencies that you have at the different positions, and with this you should be able also to constrain, for example, the potential. Now you can go like 1 kiloparsec, 1.5 inside and outside compared to the solar neighborhood, and you can track this change in shape of the phase spiral, but you do detect phase spiral, but it changes the shape, which is expected.
Okay.
So it makes sense. Yeah.
Okay. Yeah, thank you. Okay, the last question that I have now, a question that I had just emerged now that you talked about this. I don't know, maybe this is kind of going too far, but wouldn't it be possible for us to, for instance, see how does the spiral looks like in different populations? I mean, for instance, if you get old populations and young populations of stars, does the spiral change? Because I don't know, maybe this would be tracking what causes the spiral in terms of the timescales of the phenomenon.
It's very good. It's a very good question. And imagine we had perfect ages, and we can start doing beams in age and see where the star appears and where it disappears, and this will give you directly the time where this happened, right? So you would not expect very young stars to be part of this perturbation if the perturbation was very long time ago, unless the gas, as we were discussing before, unless the gas also plays a role and new stars are formed already with some perturbations. Okay, this could be. This has been done, but we don't have enough precision. So they did beams in age, and it seems that for very old ages, you don't see the spiral, but this is expected because orbits are hotter and the perturbations don't get that much imprinted. And but you see it for most of the other H beams. But the H beams you can do are like from 0 to 500 million years, from 500 to 1 gigayear. So it's very imprecise, and so it's. But it would be like the perfect clue to see the time scales, basically. Yeah.
Okay. Yeah, maybe in the future, I guess.
In the future, I don't know, maybe with clusters. We have several ideas we can try to look at, but it looks complicated at the moment.
Okay, yeah, thank you for answering.
But not impossible, and I'm sure this will be the future. Yeah.
Okay, thank you.
Thanks to you.
Guilherme. I think my last question is already answered. I was going to ask exactly if it makes sense to separate the early spectral stars of spectral type O, B, A, I don't know, and to study the kinematics of them. But you said there's no statistics enough to.
They did it by color as well, and they find a similar thing. But again, the beams are so large that. Or they did it by beams in metallicity, in alpha abundance even, and you see the expected thing. Very old cases, very old samples don't show this, and intermediate to young, they all show the spiral. So for the moment, no more precision than that.
It was very new for me. This, I think the last thing you showed, one of the last things you showed in your presentation about this break of the symmetry in the galaxy, the rotation is different above and below the disk. Is there any hypothesis, any guess why? What could cause this?
No, but you see it in simulations as well. So the exact mechanism of what is happening, we really don't understand. But it's probably part of the whole thing, right? So it's a kind of correlation between Z, B5, BZ, and R. And
right.
If you look at this, we are like cutting the phase space in different projections, but it should be the whole thing. It's just that we need more understanding, but I think it's seen in simulations, similar things. So. But they are very difficult to model in a way because we are out of equilibrium things, and yeah, I don't know how is this moving forward.
We have one more question. I think the last by Juan, please, Juan.
Hi, thank you for your very interesting talk. I was just wondering, does it has something to say, the Fermi telescope? For instance, what happened with the Fermi bubbles, that it seems to appear something that happened many years ago above and below our galactic disk. In this case, does it have some observation from gamma rays, or in your knowledge?
Honestly, I don't know. I don't know about it. Well, I heard about these bubbles, but I didn't make any connection to what I'm doing. So, what's your question exactly?
If there is gamma ray observation of above and below the galaxy in this phenomenon that you are studying, that appears to be very ancient.
Not that I know, but let me look at this. I never got such a question. Let me look at this. But not that I know. Do you have, I mean, because you are asking about
Well,
this?
the question was inspiring because what I was commenting about the Fermi bubbles, that it was seen by Fermi telescope, but something that apparently happened many years ago.
But do you know more like time scales or?
Time scales about, size scales about tens of kiloparsecs.
Yeah.
I don't know if this is the scale of your.
It could be. It could be. We are seeing it locally, but we've seen simulations that what is happening should be global. It's just that we only have data, well, locally, 2-4 kiloparsecs, but for sure it must extend beyond that.
Okay.
Okay, so let me look at it and.
Well, just a comment.
No. It's very interesting, of course. Yeah, as I said, even at the level of star formation, all these things can be connected somehow. So it's very interesting to look at other aspects that could be. Yeah, thanks a lot.
Right, so I would like to thanks Teresa again for being here, for accepting this invitation, for giving your time, your knowledge for us, for the presentation, all the interesting facts we learned today. Thanks for the discussion.
Yes, thanks for the very nice discussion. I enjoyed it a lot.
I would like also to thank everyone, all the participants, people here in YouTube, following the seminar. And we will finish the broadcast now to YouTube. If someone, maybe if Teresa has some minutes more, if someone has some more questions, can ask her from now. So we will finish it with Richard's. Okay.